A pleasure to introduce Samuel Pacitti Gentil, who will talk about four-vertex type theorems for space curves and polygons. Thank you very much, Samuel, for accepting this invitation. You can start when you are ready.
Okay, I hope that everybody can hear me. My name is Samuel Pacitti Gentil, and I would like to thank the organizers for inviting me to this event once again. And it's a pleasure for me to be here. And today I'm going to talk about four-vertex type theorems for space curves and polygons. So this will be the outline of my talk today. I will start with the original four-vertex theorem, and then I will talk about some ramifications of this very important result. So our story starts in 1909 when the Indian mathematician Mokhopadhyaya proved the following theorem. Suppose that you have a plane regular curve which is closed, simple, i.e. it doesn't have self-intersections, and moreover it is convex. This means that the interior of the curve is a convex region. If you pick two different points, the segment spanned by these 2 points is also contained in the interior of the curve. His theorem states that such curve will have at least 4 points at which its curvature function kappa attains a local maximum or a local minimum. And these 4 points are called the vertices of the curve. It will be convenient to assume that such curves do not contain any segments, otherwise this theorem would be trivial. And this theorem admits many generalizations, which were proved along the years after Mokhopadhyaya proved his theorem. This theorem can be generalized for curves which are not convex, also for spherical convex curves, for space curves, and also, interestingly, for projective curves. Our focus will be the three-dimensional Euclidean case, but it's important to notice that this theorem also has, there's a very interesting theory regarding generalizations of this theorem. Okay, since we want to generalize this theorem into the three-dimensional case, we must define what it means for a point of a space curve to be a vertex, and how can we define convexity for space curves? Because in this case, there's no such thing as interior of the curve. We are dealing with curves in space. Okay, recall that the vertex of a regular plane curve is a point at which the curvature attains a local maximum or minimum. In other words, its derivative vanishes at this point. Okay, because we are assuming that our curve is sufficiently has as many derivatives as we want. And this happens if and only if the curve has a higher order of contact with the osculating circle at this point, as we know from the theory of differential geometry of curves. So the notion of the vertex of a plane curve must be somehow related to the order of contact with some kind of object. And as some of you might be familiar with, the most reasonable candidate is the osculating plane of the curve at this point. But this means, on its turn, that the torsion of the curve vanishes at this point. This is true. When the osculating plane has a higher order of contact with the curve at this point, this means that the torsion vanishes at that point. And from now on, I will call these points, instead of using the word vertex, I use the word flattening points or simply flattenings. Exactly because it has a higher order of contact with a plane. In other words, the curve is, as we can say, flat at this point. It's not flat, but almost flat at this point. It has a higher order of approximation. Okay, now, since we have thought of a definition for a vertex for a plane curve, for a space curve, we must also define convexity for space curves. And recall that from what we knew about plane curves, a curve is convex if and only if it is contained on the boundary of its convex hull. This is an equivalent condition for a curve to be convex. Another condition that is also true for convex curves is the following. If you pick two different points of the curve, the line that passes through them intersects the curve only at these points. If the points are different, then the intersection is transversal. If the points are the same, then we are talking about the tangent line at this point. And the tangent line intersects the curve with multiplicity 2. And a third way of expressing convexity for plane curves is the following. For each pair of distinct points of the curve, their respective tangent vectors do not point to the same oriented direction. So each of these conditions define a class of curves in three-dimensional space, and these three classes of curves are not the same. So each of these were studied by different mathematicians, and each of these, using each of these notions, we can prove a theorem of four-vertex type theorem. What does it mean, four-vertex type theorem? So definition, a regular closed space curve is called a weakly convex if it lies on the boundary of its convex hull. Notice that this makes sense for space curves. And two mathematicians, among many, proved the following theorems. So Maria del Carmen Romero Fuster, which was a professor in Valencia in São Carlos, if I'm not mistaken, proved that a weakly convex curve satisfying certain extra conditions, which I will not talk in detail about these here, but we will call this genericity conditions, must have at least four flattens, i.e. 4 points at which the torsion vanishes. And 4 years later, Pacitti proved that a weakly convex curve, even without these extra conditions, must have 4 flattens. So this is the four-vertex type theorem in the sense that, well, we are not calling these flattens vertices, but they play the role of vertices that were for plane curves. For plane curves, we have vertices, and for space curves, we have flattens. And it's four-vertex type because we are proving a non-trivial lower bound of 4 on the number of flattens. So another theorem is related to the second notion of convexity, and it was studied by German mathematician Martin Barner in 1956. It proved that a certain class of curve also must have 4 flattens, and this class of curves is defined by the following condition. He says that a regular closed space curve is strictly convex. This is his terminology. I know that some of you might read strictly convex and think another thing, but he expresses this condition using the word this terminology, strictly convex. If for any 2 given points of the curve, there is a plane, there is at least one plane that intersects the curve only at these points with the corresponding multiplicities. If this condition is true for a given space curve, then his theorem guarantees that the curve will have at least 4 flattens. Actually, his theorem is more general since he doesn't restrict his study to space curves. He studies projective curves of any dimension, for any projective space of any dimension, and accordingly, his theorem is more general. But since we are focusing our study, our talk here in the 3-dimensional case, once you restrict his definitions and his theorem to 3 space, we get this theorem here. And finally, a third way of expressing convexity for space curves is given by the tangent indicatrix. So some of you might not know what is the tangent indicatrix. It is the following curve. We have a space curve, a regular space curve, and at each point of the curve, you have a unit tangent vector. It points to a certain direction, for instance, on the sphere. And as we move around the curve, this unit tangent vector traces a curve on the sphere. Since our original space curve is closed, this curve, which we call the tangent indicatrix, will also be closed. And his theorem states the following. If a curve whose tangent indicatrix does not have self-intersections, and this curve will be called a Sagre curve, because of the name of the mathematician who proved this theorem, such curve will have at least 4 flattening. Again, we have a non-trivial lower bound of 4 on the number of flattenings for a curve that satisfies a certain convexity condition. And his theorem follows actually from the following theorem on spherical curves. The tangent indicatrix of a regular space curve will also be a regular spherical curve. It will also be regular. This is the point. And inflection points of the tangent indicatrix, i.e. points at which the spherical curve has a higher order of contact with the great circles of the sphere, will correspond to the flattenings of the original space curve. Therefore, the previous theorem follows from this one here. Regular and simple means without self-intersections. Spherical curve, which is not contained in any closed hemisphere, must have at least 4 inflection points. Okay, and so we defined 3 different classes of space curves, and each of them admits a non-trivial lower bound of 4 on the number of flattenings. And 2003, Uribe proved some relations between these classes. He proves that any strictly convex curve is weakly convex, and also it is a Sagre curve. And moreover, there is an open set of weakly convex curves which are not Sagre, and there is an open set of Sagre curves which are not weakly convex. So, in a sense, the notion of strictly convex curve in the 3-dimensional case is the most restrictive one. The classes of Sagre curves and weakly convex curves are more general, and more interestingly, these 2 sentences here show us that they are interesting on their own right. It's interesting to study them and try to generalize this theorem for such curves. So, up to this point, we talked only about the smooth theory. We were talking about regular curves. A different approach to not only to the four-vertex theorem, but for lots of mathematical theories in general, is to discretize these concepts and problems. In our case, since we're dealing with closed curves, we will be talking about polygons. And it is interesting to shift our focus to this different approach by the following reasons. First of all, the theorem of polygons provides, in the limit, a theorem and actually a new proof of this theorem about smooth curves. This discrete approach allows the use of induction on the number of vertices, for instance, which simplifies considerably our proofs, and also borrows results from graph theory or combinatorics in general. And a third point, which is also interesting, and also it is the point that justifies why this is an active area of research, especially for the four-vertex theorem, is that discretizing is non-trivial. There might be different discrete results of a given smooth result, which are not equivalent to each other. Okay, so how do we discretize the theory that we have seen so far? The first one is we must define what does it mean for a curve to a polygon to have a flattening. So given a closed space polygon, we say that a triple of vertices is a flattening if the previous and the subsequent vertices relative to this triple here are on the same side of the plane spanned by the vertices of this triple. So on the left we have a flattening, and on the right we have something that is not a flattening, actually, because here these 2 vertices are on the same side of the plane spanned by these 3 vertices. And okay, up to this point, the notion of weakly convex polygons was already studied by Sadiq recall that he was the same mathematician who proved this theorem, not only for weakly convex polygons, but also for weakly convex curve. He really liked that theorem. He proved the smooth and the discrete versions. So he proves a four-vertex type theorem for such polygons using only discrete tools. This is interesting. This is important here because one of the things that I said is that it is interesting to have a theorem about polygons using only discrete tools because that would allow us to prove the smooth version using, for instance, a limit argument. Tabachnikov and Ovsienko also prove a similar theorem for strictly convex projective polygons, which imply, in particular, a four-vertex type theorem for three-dimensional Euclidean spaces using only discrete tools. It's basically basic linear algebra. It's not that sophisticated. This is common in the discrete theory of the things. The proofs simplify considerably. And discrete analogs of results, again, using only discrete tools on cyclic curves, were basically the subject of my PhD research. And I will talk about some of these results in the rest of my talk. One last thing, in the study of space polygons, it is convenient to assume that they are generic. This means that any four vertices of the polygon are not on the same plane. So here I will talk briefly about weakly convex polygons and strictly convex polygons. So an important definition is the following. A closed space polygon is called weakly convex if it's contained on the boundary of its convex hull. So here we have a weakly convex polygon, and here we have a non-weakly convex polygon. Given a generic space polygon, we say that a plane is a support plane if it's spanned by a triple of vertices of P, such that all other vertices of P are on the same side of the plane. So if you look closely at the triangulation of the boundary of the convex hull, we see that these triangles are exactly the intersections of the support planes with the convex hull of the polygon. You also say that support plane is osculating if it is spanned by three consecutive vertices of P. Notice that in this case, this triple of vertices will also be a flattening. So they proves in 1997 that a weakly convex polygon with at least four vertices has at least four osculating support planes. Because we don't want to deal with the degenerate case, such as a triangle. This is the reason why we are assuming that the polygon has at least four vertices. And also that a corollary of this result is the following. Since osculating support planes are generated by a triple of vertices, this triple of vertices, which defines an osculating support plane, will also be a flattening by this remark here. Therefore, a corollary of this theorem is that a weakly convex polygon with at least four vertices has at least four flattenings. And this is the reason why I changed the terminology to flattenings instead of vertices, because when we are talking about polygons, a vertex means like a vertex. Instead of we have a vertex, we have an edge. So the reason for this terminology here is to avoid the confusion. Okay, and one of the tools that we can use to prove this theorem is simply looking at, we could call the Maxwell's graph associated to a polygon P. Simply said, is the dual graph to the triangulation of this set here. This is the boundary of the convex hull, and this is the polygon. The proof, this was part of my, I would not say PhD research, was mostly on the master's thesis. This is a relatively well-known result. Romero Fuster, when she proved her theorem using a smooth version of the Maxwell's graph. The most important feature is that the extremal points of this graph correspond to flattenings of the curve. And then, the proof simply works by studying this graph and deriving some of its properties. But this can be done not only on the smooth scenario, but also in the discrete case. Okay, another notion of convexity for polygons is the discrete version of the theorem by Martin Barner. We say that a generic space polygon P is strictly convex if for any two vertices of the polygon there is a plane that contains both these vertices and intersects P with multiplicity 2. Multiplicity 2 simply means that this intersection is either transversal and intersects the polygon only at these vertices, or that it might intersect an edge, for instance, but you can perturb slightly the plane and obtain another plane that intersects transversely the polygon only at 2 points. There are some details here, but I'm not going into the details here. And the theorem proved by Ovsienko and Tabachnikov states that such polygons must, provided that they have at least 4 vertices, must have also at least 4 flattens. Again, their theorem is more general since it was stated for projective polygons, but our focus here is the 3-dimensional case. But the theorem admits generalization into higher dimensions if we consider projective curves or projective polygons. Both work. Okay. Now we start talking about segment polygons. But first of all, we must recall that segment curves were somehow related. Their definition was related to the fact of their tangent indicatrices not having any self-intersections. So we must define the notion of discrete tangent indicatrix in order to make sense of this new definition. Given a space polygon, its discrete tangent indicatrix is the closed spherical polygon with these vertices here, where each of these vertices is simply, what would play the role of the tangent vector, the unit tangent vector. We think it's simply the oriented edge. And here we divide by the norm just to have a unit segment. So each of these points define a point on the sphere, and then we connect each of these points with the following one, simply using the geodesic segment on the sphere. So our main definition here is the following. A segment polygon is a space polygon whose tangent indicatrix does not have self-intersections. And the theorem we proved in 2022 is that a segment polygon must have at least 4 flattens. This was part of my research with my advisor Marcus Kreiser. Some of you know him. And the proof, the theorem actually follows from a result that we'll see briefly, but in order to make sense of this, we must define another notion. So a spherical inflection of a spherical polygon here is a pair of vertices of our spherical polygon such that the previous and the subsequent vertices relative to this pair here are on different sides of the spherical line spanned by these 2 vertices. So this is an example here. This is an inflection because this vertex before the pair is on the different hemisphere defined by these great circle. The great circle is spanned by these 2 vertices. And then this other point is on the other hemisphere. So this is an inflection. And it's interesting to notice that an inflection will happen if and only if the corresponding space polygon, the original space polygon, has a flattening. So this is an important point. And another thing that is important is that the condition that these 2 vertices are in different hemispheres determined by the spherical line spanned by this pair is actually equivalent to the condition that these determinants here have opposite signs. So the most important theorem states that a spherical polygon, which is not contained in any closed hemisphere of the sphere, and without self-intersections, must have at least 4 inflections. And in order to show, the outline of the proof, we shall make use of some characterizations of these polygons in terms of determinants. We will assume from now on that our spherical polygons are such that any 3 of its points are not in the same spherical line. This is some kind of genericity condition for spherical polygons. Okay, so this is a proposition which is not hard to prove, but it says the following. If you have 4 points on the sphere, no 3 of them in the same spherical line, then these 4 points are not in the same closed hemisphere if and only if the following determinantal relations hold. We don't have to memorize this, but this is simply to just state that such condition can be encoded algebraically. This is a more compact form of writing that we just drop the U letter and write only the subscripts. And geometrically, what does it mean for 4 points not being the same closed hemisphere? We will say that this is the terminology that we will use from now on is that these points are in balanced position. In such case, they subdivide the sphere into 4 different triangular regions, and each point of the interior of each triangle will be a positive linear combination of the vertices of the corresponding triangle. So here we have a point, and its antipode will be, for instance, here. And more generally, we can say that a set of points on the sphere is in balanced position if they are not in the same closed hemisphere. A spherical polygon is in balanced position if its vertex set is in balanced position. Here we have some propositions. For instance, if a set of points is in balanced position, then any point of the sphere is a positive linear combination of points of this set. And moreover, if a set is in balanced position, then there are at least 4 points of this set which are in balanced position. And this motivates a definition. We say that given a set of points in balanced position, one of these points is non-essential if the set defined by x minus the unit set, which contains only this point here, is in balanced position. In other words, we have a set of points in balanced position. If we choose one of them, take it out, we see if the rest of the points is in balanced position or not. If the rest of the points still is in balanced position, we say that the point is non-essential. It's not essential. This is the terminology. It's not essential in the sense that it's not essential for the rest of the points to be in balanced position. Otherwise, we say that the point is essential. This is the case where we take it out, and the rest of the points then is contained in a closed hemisphere. And this is an important proposition, which states that given a set of points in balanced position, a set of points with at least 5 points, the number of non-essential vertices is greater or equal to n minus 3. This is an important result, which I will use later. Okay, we were capable of defining, to express algebraically what it means for a curve to be in balanced position, for a polygon to be in balanced position. And what about self-intersections? This proposition states that a spherical polygon has a self-intersection at these edges here, I and I plus 1, j plus 1, if and only if the following determinantal relation holds. Okay, we can write that in a more compact form, writing only the subscripts. And again, you don't have to memorize this. This is Okay, and a simple example of a spherical polygon balanced position. And in this example, we can use these determinant relations to deduce something about it, is the following. If we have, if this polygon is in balanced position, then the first proposition that related somehow the balanced position hypothesis with the determinantal characterization says to us that this is true. In other words, this sequence, if you rearrange this sequence here, has exactly 4 sign changes. But recall that a sign change in these determinants here is simply another way to say that the polygon has an inflection between these two triples. So in this case here, for a polygon, for a spherical polygon with imbalanced position and with exactly 4 vertices, the theorem that we want to prove is already true. We have 4 different sign changes here. And also interestingly, such polygon does not have self-intersections because for if it had sets between these two edges here, we would have, by the second proposition that related the condition of had self-intersections with the determinantal relations, we'll have this thing here, which contradicts the first equation, but not equation, but the first relation here. And this would be a contradiction. So this polygon does not have self-intersections. Okay. Again, to simplify terminology, we simply say that a spherical polygon is simple if it does not have self-intersections. And given a vertex ui, we define this new polygon here, q minus ui, be the polygon obtained by q by deleting this vertex along with these adjacent edges here. So we have a polygon here, we delete this vertex, we also delete these edges here, and then we simply reconnect the remaining vertices, forming a new polygon. So this would be our q minus ui. We say that this vertex is good if this new polygon is simple. If it, in other words, if this polygon here does not have self-intersections. Otherwise, we say that this vertex is bad. And an important lemma states that a polygon, which is simple and also in balanced position, must have at least 4 vertices. And this is an important lemma that we will say why this is important briefly, but just to, I think I can, the idea, I don't know if I will have enough time to explain all the details, but the idea is simply that you can, the balanced position hypothesis allows us to triangulate this sphere using only vertices of our polygon. This was made here for one of the regions determined by the polygon, but this can be done in the 2 regions. Since you can triangulate it, we simply triangulate it, and we see that this triangulation gives us a dual graph, and the vertices of the graph correspond to triple or vertices, such that the middle one here will be a good vertex. Okay, this is mainly the idea of the proof, but this is another remark. We say that it's important to notice that this balanced hypothesis is necessary. So if we have a spherical polygon which is contained in a closed hemisphere, it will not have necessarily 4 good vertices. So here with blue, these are the good vertices. And it's not hard to see that we can add more vertices to this new polygon, obtaining new examples of polygons which have at most 3 good vertices. So the problem here is that the balanced hypothesis condition is necessary. An important corollary of all this theory that we built up so far is the following. Given a set of points in balanced position, we already knew that we saw that the number of non-essential vertices is greater or equal to n minus 3. Okay? And the previous lemma stated that a simple spherical polygon in balanced position must have at least 4 good vertices. And I mean, if you look at these numbers here, we can already see something interesting. The corollary then is the following. A balanced and simple spherical polygon must have at least one vertex which is good and non-essential. And this will be important because this will allow us to use an induction argument on a given polygon. So the outline of the proof of the theorem is the following, admitting the results that we have seen so far. So our theorem states that a simple spherical polygon in balanced position with at least 4 vertices has at least 4 spherical inflections. The proof is on induction on the number of vertices. We know that this result is true for polygons with exactly 4 vertices. That was our example that we have seen some slides before. In the previous slide, we saw that there is always a vertex such that its deletion does not cause the new polygon to not lose the balanced condition and the property of not having self-intersections. So if you take it out, the new polygon is balanced and simple. And then we want to compare the number of inflections of the original polygon with the number of inflections of this new polygon. We want to show that this number is greater or equal to this one here. But this can be done, and this is one of the advantages of working in the discrete scenario. We can do that by analyzing a finite number of possible configurations, and all of them are up to symmetry. All of them are here, and if you check carefully each of these situations, the number of inflections of the original polygon minus the number of inflections of the new polygon is always greater or equal to 0, and therefore the theorem is proved. Okay, and this theorem has some applications to other spherical polygons. Here we have a discrete version of the famous tennis ball theorem, which was dubbed in this way by Russian mathematician Arnold. If a spherical and simple polygon divides the sphere into 2 regions with the same area, then Q has at least 4 spherical inflections. This follows by the fact that such polygon will be in balanced position. And we also have an improvement on the lower bound of inflections, provided that our polygon is what we call centrally symmetric. In other words, if you reflect this polygon through the origin, you get this polygon once again. So these are 2 interesting applications of our theorem. And then we turn our attention to, we will still be talking about Sager curves, but here we get another improvement, and we follow the lead by another mathematician who about 10 years ago proved an improvement for Sager's original theorem. You notice that if you have, it proves that for a C2 closed spherical curve, but we can simplify our approach here simply by stating the theorem for any regular closed spherical curve. And it states that if this curve is not entirely contained in any closed hemisphere, and if it also satisfies an additional condition, it will have we have a lower bound of 6 inflections. And this extra condition here is given by this following, this not equation here, but it's the condition is that the curve does not have self-intersections, but it doesn't have what we could call an antipodal intersection. The curve does not pass through a pair of points which is antipodal to each other. If your curve manages to avoid self-intersections and this antipodal intersection, then it must have at least 6 spherical inflections. This result is actually slightly more general. We'll talk about that about 10 minutes, but our focus here will be to discretize this result. And in order to do this, we also need a characterization of antipodal intersections given by determinantal relations. So recall that we already had a determinantal characterization for the balanced condition hypothesis, and we also had another determinantal relation, but for two edges having a self-intersection. So this was just to recall you. And then we want to have another relation that encodes the fact of the polygon not having or having antipodal intersections. So this is our proposition. A spherical polygon has an antipodal intersection at edges ui plus 1 and uj plus 1 if and only if the following relation holds. Here I'm just writing the subscripts. I think one thing that I forgot to okay, maybe it's this is I didn't say this, but this is a determinant. I said this was a determinant relation, and this here I forgot to tell you. This meant that both determinants have the same sign. They are both positive or they are both negative, and this here means simply that they have opposite signs. Maybe it was implicit here, but I should have said that before. Okay. Anyway. Okay. And this relation here is similar to the notion of two edges having a self-intersection. The difference here is that we simply shifted this subscript and with this subscript here. I mean, they are in different positions. This is the difference between antipolar intersections and self-intersections. And if we compare this relation here with the balanced hypothesis condition, we see that this will happen if and only if the set of vectors is in balanced position. Okay. Using these relations, we can prove the following proposition. That is the base case. It's a minor version of the theorem that we want to prove, which states that if you have a spherical polygon, which is balanced, and it also does not have self nor antipodal intersections, then it must have at least 6 inflections. This can be done by using all the former determinantal relations. So here we have an example of such polygon. Here I see we have depicted the original polygon and its reflected image. A polygon not having antipodal intersections is equivalent to the fact of its reflected image not intersecting the original polygon. Okay, and I'll talk briefly about the statement of the theorem and the idea of its proof. I will not go into detail here, especially because it's quite technical, but so the theorem says that if you have a spherical polygon in balanced position, and moreover, it does not have self-intersections nor antipodal intersections, then, in this case, it will have at least 6 inflections. And again, this is only the outline of the proof. It's all, again, induction of the number n of vertices. The base case was the content of the previous proposition. In principle, we have to prove the existence of a vertex such that its deletion does not cause the new polygon to not have we must prove the existence of this vertex such that the new polygon resulted from the deletion of ui is still balanced and also does not have self nor antipodal intersections. And as we saw, analyzing a finite number of possibilities, the number of reflections of the original polygon must be greater or equal to the number of inflections of this new polygon. So we must find a vertex such that this new polygon here is balanced. In other words, ui is non-essential, and also such that the new polygon does not have self nor antipodal intersections. We say that such vertex is excellent. It's more than good, it's excellent, because the new vertex, new polygon, does not have antipodal intersections as well. Okay, so this is another proposition. We say that balanced position. It states that a balanced polygon without self nor antipodal intersections will have at least two excellent vertices. And the idea of the proof is again a triangulation argument on the interior of the spherical polygon. Okay, I'm not going into detail here, and then we recall a proposition that we already knew, that given a set of points in balanced position, the number of essential vertices of X is greater or equal to n minus 3. If we denote the number of by S, the number of essential vertices, then ESS is less or equal to 3. It's another way of saying the same thing. And the previous proposition stated that a polygon without self-intersections or antipodal intersections and in balanced position must have at least two excellent vertices. Therefore, the existence of a non-essential excellent vertex is immediate when the number of essential vertices equals 0 or 1. So the really technical thing about this theorem is proving the following proposition, which states that a spherical polygon in balanced position and without self nor antipodal intersections with this condition of having the number of essential vertices being 3 or 2, they are two different cases, then in this case there is at least one vertex which is non-essential and excellent. The proof is quite technical and consists of studying separately the cases where the number of essential vertices is either 3 or 2. In each of these cases, one can prove the existence of an excellent vertex among the non-essential ones. It's more, at first sight it might seem obvious, but the problem with the proof is that it's hard to define an algorithm to detect this vertex. This is the most difficult part of the proof. I'm not going to here, but once we admit this proposition, the theorem will be proved, because this is what remained for the induction argument to work. Okay, and finally, we get to the final section of this talk. I'll try to be brief here, but we knew that Mohammed-Gomez proved an improvement on the lower bound of inflections if you allow the curve to not have self-intersections. He proves actually some extensions of Sagra's original theorem, and also his theorem that we saw some slides ago, allowing the curve to have self-intersections, which is denoted by D+, and also what he calls singular points. Singular points are simply cusps here. It's simply something like that. This is a singular point here. And notice that this is an extension of Sagra's original theorem. Sagra's original theorem is the case where the curve is regular, so S equals 0, and since Sagra's result is about simple curves, this number here will be 0. So if this guy is 0, this guy is 0, then we get again Sagra's original theorem. And so this is an extension of Sagra's original result. And furthermore, if this curve is centrally symmetric, if once we reflect the curve, it will go back to itself. Then this lower bound can be improved to 6. And remind that he also proved that a theorem that takes into account the fact that our curve did not have antipodal intersections. This theorem also admits an extension once you admits the possibility of having self-intersections or antipodal intersections. This number d here takes into account both cases simultaneously. If you have, this is actually the number of self-intersections plus the number of antipodal intersections. And I don't know, I know we have some 50 minutes. Can I get some extra minutes or just to, the summary of what we can do here, we can also discretize these results here. And we can assume, to simplify our approach, that a cusp is simply 2 consecutive inflections. And okay, and also we do that, we can state a discrete theorem, discrete versions of this theorem here. And these theorems are the following. Let I be the number of inflections of our polygon, and let d plus be the number of self-intersections of our polygon. And then in this case, we get this extension of our discrete theorem. You also have a lower bound of 4, but now we also are considering polygons which might have self-intersections. And if the polygon is symmetric, then this lower bound can be improved to 6. And finally, if we consider d to be the number of self-intersections plus the number of antipodal intersections of Q, then we also have an extension of the theorem that we talked about some minutes ago. If you have a spherical polygon in balanced position, then again, 2 times the number of antipodal and self-intersections plus the number of inflections is greater or equal to 6. So in principle, I could finish my talk here, but if you give me some extra minutes, I can try to talk. I don't know. Okay, in principle, this is a result. I talked. I don't know if you have more time.
Asma, would you like how many minutes?
How many minutes?
That's you need.
Oh, I think in principle I could finish here, but I think.
But if you like, I think it's no problem.
Okay. Okay, I just try to wrap it up in 4 minutes. Just the main idea of the proof. It's not that hard, but I'll try to finish here. So I will simply go through the outline of the proof. It's not that complicated. I will just talk about the proof of the first theorem. The other proofs follow, along the same lines. But the idea is that we simply assume that the number of intersections is 1, simply because when this number is 0, then we go back to the theorem that we already proved. And if this number is 2 or greater than 2, then this inequality is trivial. So we just have to look at this case here. We shall form from Q a new polygon, Q prime, which will be free from self-intersections, and then prove that this number here is greater or equal to E prime, where I prime is the number of inflections of the new polygon. And since this number is greater or equal to 4, the result will follow. Okay. And the idea is that given a spherical polygon, here's just a planification of our spherical polygon, but it's simply to make it easier to visualize. We can form from Q a new polygon, Q prime, and then in this way here, we must be careful not to connect. We just want to get rid of this intersection here, so we must connect this vertex with this vertex and this vertex with this vertex. If we do the other way around, then we will have something that we are not interested in. So this is not what we want. We want this thing here. And again, the previous procedure might cause new self-intersections, but again, there is no problem. You can get the following solution. In this case, instead of getting rid of the self-intersection and connecting directly these vertices, we can do like a surgery type of argument and then reconnect the vertices here. Again, at the end we will get a new polygon free from self-intersections, and we want to compare the number of inflections of the original polygon with this new polygon. And so in order to prove that this number 2 plus I is greater or equal to I prime, this is equivalent to showing that 2 plus I minus I prime is greater or equal to 0. So it is enough to study what happens to the edges near the intersection. So these are some of the situations that might happen. This shall not happen because here, if this happens, then our new polygon would have a self-intersection. And as I showed before, this procedure can be done such that the new polygon does not have self-intersection. So you only get situations such as these three here. Actually, the number of configurations is greater than that. I'm just picking some of the examples, but the idea is simply to compare the number of inflections of the original polygon with the number of inflections of the new polygon. And this can be done by analyzing, again, a finite number of configurations, which are, up to symmetry, the following ones. I mean, this is the only, these 27 cases are all the configurations that exhaust the possibilities, again, up to symmetry. And in all of the cases, if you study the number of intersections of the original polygon with the number of intersections of the new polygon, we get that this number here, in all of the cases, is greater or equal to 0. So again, the theorem is proved. And okay, and that's the idea of the proof. The other two theorems follow along the same lines. They are just take the case where the polygon is symmetric follows simply by the fact that we can do the previous procedure, but noticing that the new polygon will also be symmetric. And the other theorem that takes into account the number of antipodal intersections, again, if this number is greater or if the number of antipodal intersections is greater or equal to 1, then simple algebra shows us that the lower bound is also 6. And if the number is 0 of the antipodal intersections, then the proof is similar to the proof, and it will also follow from this surgery argument. You can detect the self-intersection, the usual self-intersections, and form from this polygon a new polygon, which will be free from self and also antipodal intersections. You must be careful. This can be done, but details that I'm not talking about. But I just want to simplify the presentation here. But this can be done, and okay, and I think this is I can simply okay. So conclusions: we proved discrete versions of the four-vertex type theorems of smooth curves, which prove our understanding of such results. Our proofs depended only on discrete tools, such as the algebraic characterizations in terms of determinants, the use of triangulation techniques, and also this cutting and pasting, this surgery, as you can say, procedure. And these same tools, on its own, are appropriate to attack similar problems for not only spherical polygons, for polygons in general, in the future. So this is it. I thank you for your attention, and I will be happy